Okay. So what Kepler is saying is all planets travel in this ellipse-shaped orbit, like a flattened circle is a good way to describe it. Oval shape, you could say. Sometimes on the regions, they'll say, "What is the shape of our orbit?" They're looking for the word ellipse, but if you forget ellipse, you could say flattened circle, or you could say oval. Be careful and do not confuse it with the shape of our planet. If you recall when we did that weeks ago, the shape of our Earth technically is an oblate spheroid, but that's not the same. So they will try to trick you on a Regents question. They'll say, "What is the shape of Earth's orbit?" And they'll put ellipse and they'll put oblate sphere. But it's not oblate. The shape of our planet is oblate, but the shape of our orbit is elliptical. Anyway, so what Kepler's saying is that we travel in these elliptical orbits. The sun is located at one of the foci, one of the focus points. It's like if you had a perfect circle, and as the lady was talking about in the video, a perfect circle needs one center of balance in the middle, right? That's supposed to be perfect, which I know it's not. An ellipse is going to have two centers of balance, all right? It's almost as if you took a perfect circle and then you start to flatten it out, the center point will split, and then it'll become two dots, and the dots will start to move further and further away from each other. And that's what's happening here. So the skinnier, as she said, or the flatter it gets, the further these foci, they get further apart, the distance between them, as this thing becomes more eccentric, flatter. This will be the sun at one foci. Students will say, "What's over at the other one?" Nothing. That's just empty space. It's just to balance out the oval shape. Okay. We're actually going to do a lab with this. So that in your kit that I gave you at the beginning of the year, that Ziploc bag, I gave you a couple of thumbtacks. Should be 2 in there. And I gave you a loop of string. So essentially, like she was showing in the video, it's going to be a little different. In this, they tie them to the tacks. You're actually just going to, I'm going to give you set distances. I'm going to say, okay, put the 2 thumbtacks, let's say 6 centimeters apart from one another on a piece of paper. You're going to take the loop of string, loop it around the thumbtacks, and then you're going to do like you see here, put your pencil inside the loop and draw an ellipse. And so we'll practice doing that in lab. That lab's coming up pretty soon. That is also on the Regents. So if we have a Regents at the end of the year, that's a skill you have to do. Same thing. They'll give you 2 thumbtacks and a loop of string. You'll loop the string around the thumbtacks. They'll tell you what distance to put them at, the tacks on the paper, and then you'll actually draw an ellipse. Now, after you draw an ellipse, you have to calculate what's called the eccentricity, which I'm going to show you there in a second. So this is showing you what the lady in the video was showing you. If you had a perfect circle, and let's say you had 2 focus points or 2 foci, we'll call them F1 and F2. They're on top of one another. So imagine 2 dots right here on top of one another. Then as you take this circle and you flatten it out, you go from that picture to this picture. These 2 foci right here would split apart, and they'd get further and further apart, to the point where you'd have an extreme line would be the opposite. So if I had a line, a straight line, the foci would now be right here on the ends. So F1 would be over here, focus point 1, and focus point 2 would be over here. So an ellipse is always going to be some shape between a perfect circle and a line. Right? This would be the most circular, obviously, and this would be the flattest ellipse you could have. Now, obviously, a planet can't travel in this kind of situation, right? If you have the sun at one of the foci, right, that would mean a planet would go straight line toward the sun, straight line back, straight line toward the sun, straight line back, which isn't the way we travel. At least I don't think so. A few definitions. So you should know what the word orbit means. It's the path that a planet takes. Orbit can be used as a noun or a verb, right? You could say Earth orbits the sun, using it as kind of a verb, or you could say, what is the shape of Earth's orbit, right, using it as a noun. Revolve. So revolve and rotation, try to keep them separate and distinct. Rotation has to do with our day, right? If this is the Earth and we rotate from west to east, that's our day on Earth. We're rotating, we're spinning. Revolve is us traveling around the sun. An ellipse, as she said, is a flat. You could call it a flattened circle. You could call it an oval, and it has two foci, two focus points. And then again, a foci or a focus point is a fixed point inside the ellipse. And again, there's two of them. So to get eccentricity, or this is the definition of eccentricity, it's how far from round is the ellipse, the out of roundness. This is a inverse relationship, which always causes some trouble with some students. So the more the ellipse is circular, the more it's closer to a circle, then that means it's less eccentric. So the more circular, the less eccentric. And then the opposite. If it was less circular, right, very, very flat, that means it's more eccentric. So the more eccentric it is, the ellipse, the flatter it is. Okay, so the more circular, the less eccentric, or the less circular, the more eccentric. So if I show you ellipses here, well, this is a perfect circle. So this would have no eccentricity to it whatsoever, right? This is the least eccentric. A perfect circle is the least. Now we're going from left to right. We're increasing the eccentricity. I flatten it just a little bit. This is more eccentric, the middle one, and this is even more eccentric. And I can keep going. I can make it, like that. That's even more eccentric. So as I move these two foci further and further apart, right? The distance here is, whatever, let's say it's a centimeter. The distance between these two might be 3 centimeters. So the further and further apart the distance between the foci, and then I get to this one, let's say they could be, 6 centimeters apart. The further and further the distance between the foci, the more eccentric it's becoming. This eccentricity value is going up, increasing. It's becoming flatter. Now, this is on the worksheet you're going to do this week. It's very easy. You're just going to take a ruler and calculate eccentricity. And this equation is on the front of your reference table. It's in the equation box. So we've covered this year so far, we covered density, we covered the gradient equation. So this is also on the front. If you look on your ESRT, you'll see eccentricity, which is abbreviated with a little e, equals. You measure two things. You measure the distance between those foci, the two dots in the middle, and then you divide that by what's called the major axis, which tends to confuse students. It's not that hard. Major axis is, think of it like the diameter of a circle, right? If I drew, let me try to use my tools here. Let's say I drew a circle. Okay, there's my circle. And I said, hey, measure the diameter of that circle. Show me the diameter. You would say, oh, right here, Mr. Rocco, goes through the middle. That's the same thing. These two terms mean the same. They just can't call it diameter on an ellipse because it's not a perfect circle. So the term diameter is exclusive to a perfect circle. So once you take a circle and then you start to do this with it and flatten it, it's still the diameter, but you can't call it diameter because it's not a circle anymore. They just call it the major axis. So it's the same thing. You're still measuring like the diameter right across the middle. So it's distance between the two foci. You'd have two dots here, right? You'd measure that distance divided by the length all the way across the major axis. When you do that, you're going to take a small number because the distance between the foci is always going to be a smaller distance, and you're going to divide by a bigger distance. Well, when you divide a small number over a big number, right, you're always going to get a decimal. And in this case, that's what you want. You should never get a whole number. It should always be 0 point some number when you divide. Another way you can abbreviate is right here. If you don't want to write out the whole equation, you can call it E for eccentricity equals little d, which stands for the distance between the foci, divided by capital L, which stands for the length of the major axis. Another way to help, I took it in their head. This way you know what goes on top, what goes on bottom. If you call this lowercase d, little d, then you will remember the little number, this distance between the two foci, always goes on the top. And if you call this capital L, that'll remind you hopefully that the longer distance, the bigger number, goes always on the bottom. So it's little number on the top, big number on the bottom. It says eccentricities are found with a ruler, right? So you're going to use your ruler that I gave you in your lab kit. And when you write out your eccentricities, very important, you always carry them out to the thousandth place. So if you think of decimals, right? Here's a decimal point. It's going to be 0 point. It's tenths, hundredths, thousandths. You always go out 3 digits. And you have to be very careful of your rounding, right? If I gave you, let's say, 0.3718, and I said, what is that to the thousandth place? You look at the 4th digit to see what you do with the 3rd digit. So if you're going to the thousandth, 3 digits, you always look at the next one over. If this number is 5 or more, right? 5 or more, what's the rhyme? 5 or more, raise the score. So if that's 5 or more, you make this go up. So 5 or more, raise the score. 4 or less, let it rest, right? So I use that rule. 5 or more, raise the score. So if it's 0.3718, it's going to be 0.372, which you might say, I know how to round. You'd be surprised in 20-something years, I have a lot of students that still mess up rounding, right? If I gave you 0.279, well, here's a good one, 2799. What if I gave you that? So now you say, well, wait a minute. This 9 makes this 9 go up, and this would have to also go up, right? So then it would be, this 79 becomes 80. So 2799, properly rounded, would be 2.280. Another thing that will come up, when you divide these numbers. So again, you're taking the little distance divided by this big distance. D, distance between the foci, divided by the length of the axis. If your calculator comes out to be 0.2, and I'll get students say, oh, Mr. Rocco, it came out to be exactly 0.2. What do I have to do? You got it, even though it's thousandth, you have to put 2 zeros here. So you'd have to have 0, 0 as your placeholder. If you don't, you lose credit. So you have to always make sure it goes out 3 places. Whether there's 3 digits on a calculator or only 1 digit, you have to put the zeros to carry it out, or you have to do this proper rounding. Okay, and don't double round. I'll have students. I'm trying to think of an example. Let's say I had let's say 0.4. Let's see, 0.49. 4, in this case it would 4999, right? How would that round? So that they're all going to round up, right? So it's going to be 0.0. What's that? 500. I was thinking of this one. So let's say it's 0.3. Here, was it 3699? So then what students will say? Oh, well, I'll round this up. I'll round that up. I'll round that up. I'm just going to go right to 0.400. Okay, you did too much rounding. Like, that's over rounding. So if you had 0.3699, you're going to make this 69 become 70. So it'd be 0.370. Again, you got to throw that 0 in there. So just be careful with your rounding. All right, so you use a ruler. You measure between the 2 foci. And let's do this as an example here. Let's say I measured these 2 distances, this distance, and it came out to be 10 centimeters. Then you measure all the way across. Again, it's called major axis, but it's like the diameter. And let's say that came out to be 22 centimeters. Then I'm going to plug in my work here. I'm going to show the equation. E equals D over L, right? That's my small distance over my bigger distance. In this case, 10 centimeters went on top. Bigger number went on the bottom, and when I rounded, I got 0.455. The other thing, when you divide these centimeters, when you have units on top of units, they cancel out. So because this was centimeters and this is centimeters, they cancel. You don't put units here. This is the one time you don't. When you're doing a gradient, you have to have feet per mile, or you're doing some kind of rate of change, miles per second or something. In this case, the centimeters cancel. You don't put units. So if a student did E equals 0.455, and then a lot of students will put centimeters here, that's incorrect. You want to get rid of that centimeter, no units. Now, your reference table lists the eccentricities, okay? So here, if you go to page 15, you will see them. And again, the rule of thumb is the lower the number, right, the closer to 0, the more circular the orbit is. The closer to 1, it's going to be 1, or close to 1, the flatter or the more eccentric it is. And so you can see if you look at all the planets, Mercury has the highest eccentricity number, 0.206. So that means you could, if we were above the solar system looking at Mercury go around the sun, with the naked eye, you could tell Mercury wasn't a perfect circle. Because that's almost a quarter, right? 250 is a quarter. So you could see Mercury. But most of the other planets, if you look, you see the first digit in the 10th place, Neptune 0.009, Uranus 047, 056, 048, 093, 017, 007. They're all very low numbers, which means, again, as the lady talked about in that short video, it's very hard to see that we're not in a perfect circle. And that's why early astronomers thought we traveled in perfect circles, but we don't. They're close, but you can't tell. This is an old reference table if you're wondering where Pluto is. So actually, when Pluto was a planet, right, you can see its number was the highest, which is why it's taken out, because it had a very high eccentricity. And so let's say this is the sun, and we'll draw Neptune. Neptune has a very low number. So 009 means when you look at Neptune's orbit, let's say this is Neptune's orbit, it's almost a perfect circle. That would be N for Neptune. Pluto, being an oval, would look like this. Well, I'll put P for Pluto. That's why Pluto's not a planet anymore, because if you took a circle and an ellipse, they would crisscross each other 1, 2, 3, 4 times, which is what Pluto does. It crosses over Neptune's orbit 4 times, and therefore astronomers back in 2006 got together and said that can't happen. Pluto is crossing over Neptune's orbit, and they declassified it. And it's really, this is the reason why. If Pluto had a very low eccentricity value, then Pluto wouldn't have an oval. It would have been a perfect circle, wouldn't be crossing Neptune's orbit, and Pluto probably would still be the 9th planet. But because it has a very high eccentricity, that's why it was taken out and not classified anymore. Okay, that's enough of that. I'm going to post this on Canvas, so please watch this video in its entirety. Go back and rewind parts that you need to hear again, just to clear up any confusion. And then you have the eccentricity worksheet where you have to print out and then use a ruler to do those measuring. So you're going to, again, be doing this stuff where you measure the distance between the foci and then you measure all the way across. I did one for you as an example. So this short distance divided by this long distance, again, always carry it out 3 places, no units. And then the other worksheet is just 10 multiple choice questions on Kepler's laws. And that'll be it. So I wish you all a very happy and healthy and safe Thanksgiving. And I'll talk to you soon. Bye.